Oh, sorry, two things today. So the first thing is image reconstruction. So we've talked a whole bunch about how our gradients and RF pulses physically do a Fourier transform of the brain and generate a signal that's a Fourier transform. And so now what we want to talk about is we've got this signal, K-space signal. How do we reconstruct it? So that's the first thing. How do we reconstruct it? That's very simple. With our original equation, we just do an inverse Fourier transform, which is basically the same as the forward one, except for one sign change. But then we need to talk about a discrete Fourier transform, because the equations I've been writing down are assuming that you have a universe that's completely empty with a brain in the middle. That's it. It's infinitely large, and then you're infinitely finely sampling the data. Obviously, that's not practical, so we're just sampling a small amount of data. We're not. There's two infinities here. So one infinity is how much, like in the case of the forward Fourier transform, how much x and y, do we go out to an infinite direction in x and y and z? But the second infinity is how finely do we sample? Do we sample like infinitely finely sampled, or do we just sample every once in a while, but still going out to infinity? So we could do a sample, like at x equals 1, x equals 2, x equals 3, but we could still go up to infinity. So there are two different infinities. And how far do we go out, and then how finely do we go at each point? It turns out that second one is the one that creates problems for us, more so than the brain in an empty universe. So let's just write the equation up again for generating the signal, and just do a 2D one. So we have this a particular point in K-space, a particular data point, at a particular spatial frequency in the x direction and spatial frequency in the y direction, is just equal to summing across all y and x in the brain of what the brain proton density is at a particular point, times these sine and cosine stripes. So this is minus I 2 pi, and then we're adding the exponents instead of multiplying to e to the minus i's times each other. So this is whatever the kx is times the x coordinate plus whatever the ky is times the y coordinate. And then we're summing across all x and y. So what's doing this again? So this is the RF coil sig as a result of phase sensitive detection, because it's a complex vector that's coming out. And then what does the sum? The RF coil does this. It's a complex sum because it's summing these. It's effectively summing, because of the phase sensitive detection, it's summing these vectors, the local magnetization vectors at each point in the brain, just adding them up tip to tail. This thing is our real brain. That's not complex. It just has only real components to it. And then this thing here in the equation, so the equation is perfect sines and cosines. So that's the perfect cos and minus sine. So that's a problem. So there's two things here. This is equation, and then here's reality. less than perfect. So the equation says we stamped on a spin phase stripe that's exactly perfect. But in reality, we turned on the gradient, and the gradient isn't completely linear, and there's local magnetization problems, and so we didn't do something perfect. So when we reconstruct, however, we assume that we did something perfect. So how do we reconstruct? So basically, to get our image, which is going to come back complex typically, so at image xy, we just do exactly the same thing again. And so, except now we're summing across all of k space. So here's summing across all of ky space. It's what that double integral means, like for every combination of kx and ky. So it's kx times ky number of things in here that we're summing across. We just take that signal that we just recorded up there, and so at kx and ky, and we do exactly the same thing. We just multiply it by sines and cosines. The only difference is the plus. So that's an inverse Fourier transform. And sometimes people flip the x and the kx. We can do that to sort of indicate you're in sort of inverse Fourier transform. It doesn't matter, they're mathematically equivalent. Y, ky. And now we're summing across all of k space, all of spatial frequency space. And so what we've done is we've just taken this guy and just put it in here. And once again, what the equation says, is, here's, equation, perfect cos and minus and sine, positive sine. So that's going to lead to some of our problems, because we've assumed that what we did was the equation, but actually we sort of did something that's less than perfect. And it's possible to actually sort of fix that. You can actually try to measure what did we actually do. We didn't do these perfect spin phase stripes, they're slightly bent. There's ways to measure that, and we'll talk about that. I'll talk about in the advanced class. There's actually sort of a way to measure and model the imperfect stripes and all the various things, all the various imperfections, because what we'll see is that, you can sort of, this thing is just a linear sum. It's basically a linear matrix multiply. You're basically sort of, you could sort of visualize this as basically just, because of this sum right here, you can visualize it as this is just a matrix operating on a vector to generate another vector. And so you can visualize this as a linear inverse. You can just visualize this as a linear operation, and then you can make a matrix and invert it. So we'll talk about that in one of the advanced sessions. So you can view a Fourier transform as just or an inverse Fourier transform as just a linear inverse, because it's just all sums, just multiplying and adding. So it's all nice and safe and linear. Okay, so that's our basic reconstruction. So this is, generate signal, make signal, and then recon. So that's very simple. In reality, the way you do it is, this is just has to do with how the Fourier transform works. It's actually done as just two 1D Fourier transforms. So this was the 2D Fourier transform example, 2DFT. Could be 3D, but this is, you would add another Z for 3D, but we'll just do 2D. So how do you actually do it in real life? So in real life, well, we should say one thing about this complex business. So what happens is, if everything was perfect, we should get back a real brane with no complex part. So, here's the signals that go in. So you've got a signal going in from the signal that you generate, which is, it's got the real and imaginary part from the phase-sensitive detection. And then when you do the reconstruction, what you ought to get back are just vectors along, the x-axis with no real part. But in reality, you get vectors, that have a complex part. And say the phase is off enough so that the vector comes back like that. In that case, if you just take the real part, you're in a world of pain there because you've got 0. And so typically what is done on the scanner is you just take the amplitude. Just take the amplitude. The amplitude won't be messed up. So you'll have a nice big number for the amplitude. Whereas if you just took the real component of it, because you know that the brane ought to be real if everything was perfect, you could end up with 0. So the image will look like a mess if you actually look at just the real component, even though it should be real. And so that's why on the scanner you're always looking at the amplitude, and the phase angle is thrown away, whatever the phase angle was. So here's the phase angle. So we just toss the phase angle and show you or sometimes we save it because it has some information about what went wrong with the magnetic field. Okay, but how do you actually do the reconstruction in real life? So if you take that reconstruction equation, what does it look like? It looks like, signal kx, ky, and then we could break this one up into 2. So, I 2 pi x kx times e to the I 2 pi y ky, summed across all kx, ky, all spatial frequency x and y. But what we can do, if we take this guy and stick him in here, you can see that that's just a 1D Fourier transform. So if we just write that out again, so here's summing across ky and kx. So if we write it out again, we could write it out. We can just take the ky out here, and then what we're doing here is a 1D Fourier transform. So it's a 1D Fourier transform, but with a 2D image point. So here's the image, a 2D k-space point. So here's kx, ky. So it's one point in k-space, but it ranges across, all x and y spatial frequency, and then just times our, I 2 pi x kx. And here's our little integrating small bits of kx. Okay, so that guy's just a 1D. This guy's just a 1D FT. But it's done across all y. For 1, so basically for 1 ky, let's do a 1D Fourier transform. And then we take the output of that and Fourier transform it again. And so then we just Fourier transform it again. What is that? Just multiplied by, I 2 pi y ky summed across all dky. So that's how you actually do it. So what does that mean? So what that means is you start off with your k-space data. So start off with your k-space data. So we'll make 4 of these. So you start off with your k-space data. So there's your k-space data. And this is, kx, ky, k space data. So this is, kx in this direction, ky in that direction. And then we just do a 1D Fourier transform. This is the way the scanner actually does it, because it's actually more computationally intensive to do this 3D Fourier transform. And so what do? You just take that data and do 1D Fourier transforms going in the x direction. That's the meaning of this first equation. So that's this. So we do a whole pile of 1D Fourier transforms just going across in the x direction. And so what do you end up with? So you end up with a strange beast, which is, it's an image in one direction. So in this direction, it's an image. But in this direction, it's still k-space. So that's kind of sort of a little disturbing. So it's still spatial frequency in this direction, but in this direction, it's actually an image. And then all you do is do this second Fourier transform. So this second one here says, let's just Fourier transform it. Take that data, which is sort of half k-space. It's sort of a half k-space and half image, and just Fourier transform it again, line by line. And then you end up with a brain. So you could do the same thing for, 3D Fourier transform. So you would take your block of data, do 1D Fourier transforms across it, in one axis, and then 1D Fourier transforms across another axis, and then 1D Fourier transform in yet another axis. So because it's this simple linear transformation, you can do that. At first, it's just kind of like, it doesn't make sense. But you can see how the equation, you can easily just write this thing out as two 1D Fourier transforms. So this means we're doing just 1D, and then we're doing another 1D. So that's how it's actually done on the scanner. So you just do a Fourier transform in one direction, line by line, and then a Fourier transform in the vertical direction, line by line. And that's actually computationally a lot more efficient way of doing it because of the fast Fourier transform. Okay, so any questions about this? But we're still doing infinite Fourier transforms. So now we have to talk about, well, what if we didn't do something that was infinite? And so now we have to write out our Fourier transform as a discrete sum. And this is what's actually really done in the scanner. It looks almost like the regular Fourier transform, except we have to have additional variables for how many points are we doing, how far out in spatial frequency space are we going, and then also what's the spacing between what's the spacing between our points. So there's two additional things added to this. And I'll write it out the way that, I just explained, where it's basically two 1D Fourier transforms. So our image, our discrete image at discrete x and y, and I'm going to use m and n for our kx and ky discrete steps. So these are integers, like 1, 2, 3, 4. And then m and n for the total number, the number. the number of kx and ky. So that's what the m and n are. So what is our Fourier transform? It's now instead of an integral, we use this capital sigma for meaning sum. So we sum across all the n, the following thing, and the following thing is a 1D Fourier transform. So here's our 1D Fourier transform across all the m direction. That's the kx direction. And what are we summing? We're just summing our signal, a complex valued signal, at a particular n and m, integer n and m, instead of like infinitely finely sampled n and m. And then we're multiplying by e to the I 2 pi. Now we've got some additional complexity. We got n here, which means like whatever the current value of n is, integer value of n is. And then we have another thing, which is the delta delta kx. So that's the spacing in spatial frequency space to our next sample. And then times x. So there's a lot, there's like 1, 2, 3, 4, 5, 6 things in there now. And then now it's multiplied by that delta kx over here. So instead of like dx, which would be like an infinitely small little chunk of x, now we've got an actual sort of like, a certain amount of kx, like say spatial frequency, like 1, the difference between spatial frequency 1 and spatial frequency 2, because we're not doing all the ones in between. Okay, so that's our first 1D Fourier transform, and then we have to multiply by our second one, which is the same, I 2 pi, but now it's m times delta ky times y multiplied by delta ky. So what's going on here? So when we multiply n times delta kx, that means for a given integer number in spatial frequency space, we multiply by the interval, and what we get out of that then is basically what we would have had in the previous integral equation as just kx. So n times delta kx just tells us what the kx is, and same for here. So this is just ky. Okay, so that's the actual way we reconstruct images. That's a discrete Fourier transform. So now the problem is what happens? What hell breaks loose when we actually have a discrete Fourier transform instead of the empty universe with just a brain in it? So we'll start off with the empty universe with a brain in it. So if we, in the limit of going to extremely tiny delta kx's and n's that go up to infinity, then we get our original correct infinite k-space. And so here's our original infinite. So what does that look like? So that looks like a brain here. And normally you sort of think of the brain as having, there's a finite image on the scanner. The field of view, you have some idea of like there's some sort of field of view. Well, what does that mean? But in this case, we're just saying, it goes off to infinity, and we're sampling infinitely finely. And if we just do like a, oh, I forgot to put space here. Yeah, so, so on this side, we're doing space. And on this side, we'll be doing spatial frequency. That's our column headings here. So some things are easier to illustrate just in 1D because I need just like a simple 1D graph. And so if you think of this as a 1D Fourier transform, what does it look like? Well, you've got sort of black, and then you've got a brain, and then black. But it goes off, goes off to infinity. So this is 1D example. So, so if we do a Fourier transform of that, here's going back the other way, ft minus 1. So what does that look like? Well, it's kind of a boxcar function. The brain is more or less a boxcar function, black, brain, black. And so what's it going to look like? What's the Fourier transform going to look like? Well, it will look more or less like a sinc. So, what's the sinc function? That was like S-I-N-C. It kind of looks something like this. It's got a central peak and it sort of falls off if we look at it in 1D. A 1D example. So what does that look like in 2D? Our 2D K-space. Well, it's an infinite 2D K-space, of course. So it's going to look like a whole bunch of stuff in the middle, and then there'll be little ripples in K-space. And when you do the problems, you'll see those little ripples. You'll see a big spike in the middle, but then as you go out to higher spatial frequencies, it'll be brighter, darker, brighter, darker. Little sinc-like ripples. It won't be exactly like a sinc because it's actually a brain, but it looks quite a bit like a sinc. And that goes off to infinity, and so obviously not practical. But if we take that data going off to infinity and inverse Fourier transform, we just get a brain. We just get a universe that has nothing in it but just a brain. So that's so now what happens? This is kind of the most counterintuitive part. So what if we go out to infinite spatial frequency, but discrete samples? So now what we do is we go all the way. We're still going out to infinity, but we're only sampling. Let me put this down a little bit lower. So here's our brain. And our brain looks the same way over here in 2D. And so, but instead of, on this end, instead of getting a continuous sinc, what we get is a sampled sinc. So here's the sinc envelope. If it was continuous, and all we've done is we've sampled it. So we get a bunch of little individual spikes with zero in between, because we're still sort of visualizing everything as if we were in infinite space, but now we've sampled it. And what does that mean? It means like we've taken an infinitely fine thing and we've just taken data at intervals and then had zero in between. So now we got like zero in between. That's how we can sort of figure out what the effect of this is going to be by still living in infinite land, but sampled infinite land. Okay, so what will that look like? That will look like, our 2D K-space is just going to look the same as before, except that it'll be on a grid. So there'll be, whereas this one was infinitely finely sampled, so there'll be a grid, and it's, it'll look the same way. It'll fall off as you go away from the center. but it'll just be on a grid. Okay, so that was the forward Fourier transform, where we did everything as before, but we just zeroed out some of the data in between. So now what happens if we go the other way and inverse Fourier transform this grid with zeros in between it? That's when the hell breaks loose. And so what happens is you get a whole bunch of replicas. These guys are called, so when you Fourier transform that, we're still infinite. You'll end up with this whole giant grid of brains. Like this. They're all spaced the same space apart. These are called replicas because they're exactly identical replicas. And what causes that? So what causes it is the discrete sampling, not the sort of infinite spatial frequency question, because we're still going out to infinite spatial frequency, but we've only sampled like spatial frequency 1, 2, 3 instead of 1, 1.00001, 0.002. We just had this sampling interval. And so strangely, that's what happens. So we'll try to sort of get a handle on, why that happens. But we've got 2 more cases to do. So 2 more cases. So what about, non-infinite and discrete? So we could cut off our sampling. So do exactly the same thing. So we take our brain, which kind of looks just like that to start with, and Fourier transform it, but this time we're still going to do an infinite Fourier transform, but we're going to make it finite by making everything else 0. And so how would you do that? What you would do is, so this is still infinite, so you're still getting little arrows that go out, all the way out here. So in that case, what we would do is we've got our sync envelope here like that. And we would still be sampling the center of the sync envelope, same spacing. But then we would multiply this by a boxcar. So, multiply by rect. So we multiply our sampling. So we're still sampling out to infinity, but we just zeroed out. So it's all 0 out here. That's how you can sort of mathematically analyze what the effect is going to be. Okay, so now what happens if we inverse Fourier transform that? So let me draw some little lines in between here. So there's this guy. Make him go all the way. Okay, sorry. Let's make that one up a little bit higher. There we go. So now what happens when we inverse Fourier transform it? We're going to get something that has kind of a sink in it. So you can think of this thing, we multiplied by the boxcar. So remember, like this Fourier transform, convolution theorem that multiplying in one side is like convolution in the other. So when you multiply in this side, we're going to convolve with what the Fourier transform of this looks like. And so what does that do? So instead of getting so here's what we should have gotten. Instead of getting that, what we'll get is something that looks like it's been convolved with a sink. And so the sink will sort of average on a flat part. If you convolve with the sink, it just averages out to a flat. But where there's an edge, what will happen is there'll be these little ripples like that. There'll be little ripples at the edge. And, sometimes you call that ringing. It's always there. So if you look at any image on the scanner, you'll see these little fringes around any sharp edge. If you're just in a flat part, you won't see it. Like if just the flat background or like, a piece of the gray matter, you're not gonna see it. But where anything comes to an edge, there's going to be these finite ripples that you cannot get rid of. They're called Gibbs ringing. Call it Gibbs ringing. And unfortunately, their size even if you sample more finely in spatial frequency space, it makes the ripples narrower, but it doesn't change the amplitude of them. They're always the same amplitude, irritatingly. And this is an important thing for interpreting an image, because when you look at an image, wherever there's an edge, you're going to get this ringing going on. And what causes that is different than the replicas. What causes that is the fact that you're not sampling out to an infinitely high set of spatial frequencies. So you still got the replicas. So, you still got the replicas in this case. There's another brain over here. Another brain up, another brain up here. So, still got the replicas. So, last but not least, what happens if we don't sample rapidly enough in K-space? And so this is the getting to the really counterintuitive part. So, non-infinite and discrete. So that means just sampling, but too big delta kx, delta ky. We'll just do. I think in my notes I just did too big delta kx. Okay, so now we've got our brain, and we do a Fourier transform of it. And the only difference is that we're spacing out the samples of kx and ky a little bit wider. So it's exactly the same thing again. It's a sink. Here's our sink envelope. Same sink envelope. But now instead of sampling, so here was this distance here is our delta kx. So let's just make that distance bigger. So we sample the center of K-space, but then we sample, we're not sampling as often in K-space. So this is delta kx is up. So we made that bigger. So now what happens when we reconstruct? So when we reconstruct, what happens is the replicas intrude. So we'll have our brain here with a little ringing in it. There's our brain with a ringing. But the problem is, now what's going to happen is we're going to get another replica, and it'll be too close in. It might be like right about here. So what does that look like, when we look at a brain? So what it looks like, we'll still have the whole brain here, like that, but then we're going to have another one that is sitting on top of it, like that. And there'll be another one. So this other one, if we sampled the same spacing in kx, that one will not be overlapping. But then there'll be another brain over here like this. There's this other one over here like that. So that's what happens if we do this out to infinity with our same sort of sampling limits in here. So we've multiplied by a rect, just like before. The only difference was we made the sampling in kx, we spaced it out a little bit. And so what effect does that have? It causes the replicas to intrude, but what do you actually see on the scanner? So what the scanner does, the scanner says, I'm going to just give you something that looks like this. I'm just going to give you one copy that you could use to tile all these replicas. So, and that's called the field of view. So this guy is the FOV, the field of view in the x direction. And so what does that actually look like on the screen? It looks like on the screen like you've wrapped the brain, or you've folded the brain around. So let's just draw it out. Not too much space. So let's, I'll draw it out here. So what that will look like is you'll have, one copy of the brain like this, but the front part of it will be hacked off, like that, and the back part of it will be hacked off. And then there'll be the front part from the next replica, which is sitting there like that, added on top of the brain. And then you'll see the back part of this guy added on top of the brain. So that one belonged to this replica over here. And this was the frontal lobe of this other guy. Like that. But what you'll see on the screen is this wrapped up brain like that. And so that's what it comes from. It comes from these replicas that were caused by the discrete sampling. And so what does that imply? That kind of amazingly implies that, what controls the field of view? So what controls the field of view, the non-overlapping field of view, is, these guys here. This thing here. That actually controls the field of view, surprisingly. So this, and you have like separate x and y versions of them. So that's actually what the field of view is, amazingly. X, field of view, y. So it's not something to do with any kind of how, is there some little magnifier in there or something? No, it's just how rapidly you sampled the k-space. Amazingly, that's actually what causes it. So, okay, so any questions about this? It's very strange. When I first, this was I knew there was something called field of view, and sometimes I knew there was kind of wraparound, but I had no idea what really caused it. And what really causes it is the closeness of spacing between your spatial frequency samples. And the closer you space, the more non-overlapping space you have. It's like a Fourier transform situation where it's kind of the inverse. So if you space really closely, that's how you sample the exact same range of spatial frequencies, but sample them more finely, and then you'll push the replicas out. And the way you understand it, like I said, is to take an infinite Fourier transform case and then multiply it by a sampling function, so you zero out some of the values in between. Or the way you understand this ringing is you do an infinite Fourier transform, but just multiply it by this rect function. Okay, so any questions about strange life in discrete Fourier land? So we always have to deal with this because we're always dealing with a finite number of samples and a finite spacing between our spatial frequency samples. This guy?
No, the S vector.
The what?
The S vector in the double summation, the S of n and n.
Over here?
One more to the right? Yeah.
Oh, this guy?
Yeah.
Yeah, you're discretely sampling that guy, yeah. Is that what you're asking?
Yeah, so the S that's the discrete thing as well.
Yes, that's the discrete, yeah. I mean, you could think of it as kind of infinitely finely sampled, but you're only picking it up. Like for the purpose of this kind of argument, you could sort of think of it as infinitely, it's got some kind of infinite reality, but you're actually only sampling at, spatial frequency, kx equals 1, and then spatial frequency kx equals 2, or whatever. It could be, the interval could be whatever you set here. So you could sample every half a spatial frequency, like 1, 1.5, 2, 2.5, but you're sampling at discrete points instead of, yeah. So this sum is not an infinite sum, yeah. And then you're just sort of picking out individual points out of the infinitely fine Fourier transform. So to get some, so there's two ways we could use the convolution theorem here, which is like convolve in one domain equals multiply in the other domain. So the one I'll go over is where the replicas come from. So, but you can also think of where the Gibbs ringing comes from, because that's the same argument. So where the replicas come from, so if we start with like space over here and spatial frequency on this side. So if we have, there's our brain in space, and when we Fourier transform that, that's a rect-like function, sort of like a rect function. If we just do 1D Fourier transform of it, we get something that sort of looks like a sink. So if we take this thing and multiply it, so if we multiply it by a bunch of spikes, so this is our sampling function, bed of nails function. So it's an infinitely finely sampled function, but infinitely finely described one, but it's just got a spike where you sample, and then there's a gap which is all 0. So that's how we sort of model sampling our k-space signal, because we just take discrete snapshots at a particular time. So like, there's this continuous, reality is infinitely finely sampled, and so there's this infinitely finely sampled signal coming out, but we just go, let's just sample at that time and then sample it at that time, just take a snapshot at that time. So this is how we mathematically model the sampling. And so what we're going to get is, what we actually use in our discrete Fourier transform. So it'll be this, sink envelope, but we're just discretely sampling it. So there'll be like, just a point here, with zeros in between. So there's all our discrete samples. So the problem is, how do we sort of figure out what happens when we un-Fourier transform this thing? And so the convolution theorem says if you multiply on one side, you can convolve in the other side. And there's a few cases where convolution is very easy. And one of them has to do with when you have spikes. And so now we can look at, what is the inverse Fourier transform of this guy to get into the other domain. So to use the convolution theorem. So here's ft minus. So if we inverse Fourier transform that thing, what do we get? We get some spikes again. And the spikes are basically spaced out like that, and etc. They go on for infinity. And this works like a regular Fourier transform in that if you make these spikes closer together, these guys get further apart. And then now we're in this side, so we're going to convolve instead of multiply. And if we convolve that, what it does is, since this is a very simple thing, remember convolution is just pretty much like correlation. So basically what will happen is you'll just make another copy wherever there's a spike. So you'll make a copy here, and you make a copy over here. And another, so you make it, so these are the replicas. So, because if you think of convolution, you kind of think of convolution like a Photoshop filter. And if this thing is if these spikes are your image and you convolve with a little boxcar, it's going to sort of smear out the spikes. So it's kind of very intuitive. You just sort of make a copy of whatever that thing is, wherever you've got a spike. So basically these are the replicas. Now you might have heard of something similar to this with, like you might have heard of the Nyquist theorem. So, or if you're sampling an audio signal. So say if we have an audio signal like this, which has a bunch of different frequencies in it, and then we sample it, you probably know, like if you don't sample finely enough, you're in trouble. So if there's some very high frequencies in there, you can run into problems in estimating what your frequency content is. And so there's two ways to deal with it. One way, you can just filter out too high frequencies, or so you could just actually just like absolutely remove them, or sample faster. So there's two options. You either sample fast enough so you can capture the high frequencies, or filter them out. One of the two. But if you don't do that, and generally, the Nyquist theorem says you have to sample at least twice as fast as the highest frequency. Otherwise, you're going to run into trouble. And what trouble do you run into? You run into replicas in the frequency domain. So what we've been talking about here is this very strange replicas in the non-frequency domain. We said, like, if you don't sample fast enough here in the spatial frequency domain, you end up with replicas in the space domain. This is just exactly the inverse of that. This says, if you don't sample fast enough in the time domain, this is our time domain, then if not, if you haven't done one of these, then you get replicas in frequency domain. So when we Fourier transform that, if we say we had a situation where here's frequency now, not space or time, so frequency, and say our range of frequencies looks something like this. So that's our range. That's the frequencies that we found in this signal. If we haven't sampled fast enough in time, what's going to happen? We're going to get a replica. So here's another copy of the frequency spectrum. So and there'll be another one over here too. Another copy of the frequency spectrum like that. intruding. So this is a replica of frequency spectrum. And what does that mean? That means, and what will our field of view be? Here's our field of view in frequency space. But what's going to happen? Well, it means that say here was some high frequencies that were too high because we didn't sample fast enough. And so say this was like frequency 300. So what's going to happen is it's actually frequency 300. That's what frequency it actually is. But it's going to appear as like say frequency 3. It's going to be added on. There is some frequency 3, and it'll just be added on to frequency 3. And so our end result will be there'll be a spike. This thing will be added on, so there'll be a spike in our spectrum like that because those two will be added together. And what will happen to frequency 302? Here's 302. That's going to come out as frequency 5. So you'll have, so that whole spectrum of frequencies will wrap around. Same phenomenon as this phenomenon here, where we were not sampling finely enough in the frequency domain, and that ended up with replicas in the non-frequency domain. But you have the exact same, everything in Fourier land is kind of like mirror image, and so you have the same thing. If you don't sample the signal fast enough in the non-frequency domain, time domain, and then when you Fourier transform it, higher frequencies can wrap around to lower frequencies and vice versa. So that's going too quickly, but that's like this Nyquist idea that in order to avoid this, sample faster, Nyquist at least 2 times max freq. So if you do that, then you'll avoid the wraparound business. Okay, so we're powering through engineering signal processing here. So any questions in the last negative 10 minutes? So the bottom line for MRI was that what causes the non-repeating field of view, the width of that, and what causes it, sort of strangely, is the spacing between our spatial frequency samples. And so in order to widen out our field of view, all we have to do is sample the same amount of spatial frequency, but just go finer. That means more data points. So we got to collect twice as many data points. And then that will have the effect of pushing the replicas out and stopping the wraparound. And so these are weird things that happen in Fourier land. But this kind of argument is, you can use this for all different kinds of signals, audio signals, or images coming out of a camera. You might want to do Fourier transforms on them. So there's many different places where you might want to use this same argumentation. This way, I sort of knew about this. You have to sample fast enough, or you can accidentally sort of misidentify a higher frequency as if it was a low frequency. I understood that part, but this part is exactly the same thing mathematically, but it's completely weirdly different, where it just has to do with sort of sampling in the frequency domain instead of sampling in the time domain. Okay, it's going okay out there? Sort of makes sense? Final questions about the image reconstruction or the discrete Fourier transform? And so from now, all the homework problems are using the discrete Fourier transform. Okay,